Hello everyone. In this tutorial we are going to learn how we can convert a ER diagram into a relational schema. So what we'll do, we'll start with a ER diagram. We'll convert it into a number of tables and we'll also create some kind of relationship between the tables such that all the constraints specified by the ER diagram can be maintained, and also we can minimize the redundancy. Okay, so let us go for some examples. First we start with strong entity sets. So we are having entity sets called as student, right? So these are two alternative representation of entity sets, right? So it's a student entity set, this is also student entity set. So having the same attribute, enrollment number, name and contact number, right? Now our identifying attribute or primary attribute is enrollment number, right? So how you can create a table format? So we can create a single table out of it. So that's enrollment number, it's a student schema, right? Having the attribute enrollment number, name and contact number, and the identifying attribute, right, or the primary attribute becomes the primary key over here. So this is the primary key. So here an example is given. So we are having enrollment number 101, the name is Rajkumar Misra and contact number is 222222. So I am taken some arbitrary contact number. Similarly 102 Sanat K Roy 333333. So these two are two entities inside my entity set student, right? So student is now a schema and this is the particular instance of the student schema. Okay, consider again the same entity set student. So now the only difference is the name is given as a composite attribute, right? Okay, so enrollment number, which is underlined in both the cases, which is the identifying attribute or the primary attribute of the table, which is a simple attribute. Contact number also is a simple attribute, whereas the name is a composite attribute which is having three components: F name, M name, L name, which are representing the first name, middle name and the last name, right? Now how this entity set can be presented as a relation? So the student relation, enrollment number is the primary key. Now instead of having the name as an attribute, we present each of its component as an individual attribute in my table. So we are having F name, M name and L name, and contact number as a simple attribute which will come as it is. So this F name, M name and L name, they are together representing the name, but they are presented in the table in form of individual attributes, right? So if you look at the entries in our tables, so these are basically example entries. You can see 101, F name Raj, M name Kumar, L name Misra. So I took a contact number 222222 for Raj. 102 is another enrollment number. Sanat is the F name, K is the middle name, Roy is the last name, and this is the contact number. Okay, next we'll consider the composite attribute along with a multi-valued attribute. So we are considering the contact number is a multi-valued attribute such that each of the student can have more than one contact number, right? The simple way to represent it as a single table, we can think a presentation like this: the enrollment number, F name, M name and L name, which we have discussed already. Now this is contact number. So we are putting the contact numbers, all the contact numbers over here in a comma separated way. So what will happen in that case? So if you present this, all the contact numbers in us as a single field, the problem will happen. The queries with search or update becomes extremely difficult. Whenever you write an SQL with a where clause, it will be very difficult if you have a column which is having multiple entries with separated with a given delimiter. So what we should do in this particular case? So what you're thinking, for each of the contact number will create a separate row, right? So that's why as 101 having two contact numbers, we have created two rows. So all the attributes values for 101 basically repeated twice because it's having two contact numbers. Same for 102, all the informations other than the contact number are repeated thrice because there are three contact numbers. So this because this portion of the information dependent on the enrollment number. Here also the same thing happen. This portion of the information dependent on the enrollment number. So that's why for each contact number, when I have to repeat the enrollment number, this information also gets repeated. So you can understand that will create lot of redundancy into our table, right? So suppose a particular student having 5 contact numbers, in that case all the information about the particular student has to be repeated for 5 times, right? In 5 tuples. So the better way to design it, decompose the relation into two particular relations. How we can decompose? First, the first relation, say it's a student relation having the primary key, enrollment number, and other non-multi-valued attribute in single valued attributes. So we are having the F name, M name, and L name. So this creates one relation, and the primary key of this table or the actual table or actual relation along with the multi-valued attribute creates another relation. So this is the second relation. So we are having a primary key which is a composite primary key. So you can see over here, for each contact number the enrollment number is repeated. So here also you can see it's repeated, but this particular information you don't have to repeat. So it saves lot amount of redundancy, right? So in case of multi-valued attribute, we'll decompose the table. Now along with the composite attributes, multi-valued attributes, we'll also consider a derived attribute, which is age, right? So age basically derived from and a simple attribute, that's date of birth, right? So whenever we are given with the date of birth, from the date of birth we can calculate the age. So this is the base attribute, this is the derived attribute. Show it like this. Now how we can present the derived attribute in a table? You need to remember the age of a student will be changed every year, whereas date of birth is the information which is fixed. So if we have the date of birth stored inside our database, we can calculate the age whenever it is required. So normally we do not keep the age stored into a database or stored into a table. Thus, what can be our representation for our tables? So as we have seen, we'll have a student relation which will have all the single valued attribute. So that's the enrollment, primary key, enrollment number, F name, M name, L name, which are the components of the composite key, which is name, and the date of birth, which is also a single and simple attribute, right? Okay, so let us see over here. the enrollment number and the multi-valued attribute. This creates our second relation, which is contacts. Okay. Next, we'll consider the relationship between the entity sets, right? Which will be done in terms of relationship set. So, between the student entity set and the course entity set, we consider a relationship set, that's a enrolls. So there is a many-to-many relationship between the student and course via enrolls, right? So we say a student can enroll for multiple courses, or a course can be opted by multiple students, right? So we need to remember the cardinality. The minimum it is 0, the maximum it is n. 0 and n. So that means a student can enroll for 0 to n number of courses, whereas a course can be opted by 0 to n number of students. Now question is how we can represent it in terms of tables. So whenever we are having a n to n or a many to many situation, we also create a table for relationship set. So look at over here. For student, we are having table. We have already discussed how to create it. It will have the student number and the student name. We'll also have a table for the course, which is having the course number and the course name. Now, the primary key of the tables, primary key of the entity sets will become the attribute of the tables corresponding to the relationship set. So that's why the enrolls, whenever converted into a table, it will have two attributes. The primary key of the student table, that is student number, and primary key of the course table, that is the course number. So this is the table which will create for the enrolls, which will have the primary keys, right, of the corresponding entity sets. So let us go for an example. So we consider the student table. We are having two students, Raj and Sanath. Their student number are 101 and 102, and there are two courses, computer science. Course number is CS101. Mathematics, the course number is MT110. Now, I say 101 and CS101 is a tuple in the enroll. So what does it mean? It means 101 Raj got enrolled for the course, that's CS101, that's computer science. Similarly, the 102 Sanath has enrolled for CS101, that's the computer science. Sanath has also enrolled 102 for the course mathematics. You have to understand this Raj has enrolled for one course, whereas Sanath has enrolled for two courses, whereas the course computer science having two students, the course mathematics having one student. But how do I represent a course do not have any student? A course do not have any student because it is 0 to n, you need to remember, right? So if I want to say the mathematics doesn't have any student, I can simply delete this entry. So MT110 doesn't have any existence inside the enrolls table, means this MT101, this particular course is not participate inside the relationship with the student. That means there are no enrollment for mathematics. Similarly, if I want to say a student is not enrolled for any course, right? So how we can say that? Suppose I want to say the Raj is not enrolled for any course, so I can just delete this tuple because I'm having only one tuple belongs to 101. So if 101 is not there in the student number column over here, that means this particular entity is not participated in the relation. That means this 101 Raj is not enrolled for any course. Now what if the relationship having an attribute, right? This is called a descriptive attribute. It specifies the date, the enrollment date, when a student got enrolled for a particular course. Now, when converted into table, this descriptive attribute becomes an attribute inside the table that's enrolls. Means it becomes an attribute for the table which belongs to the relationship set. So as you have seen, this is our student table, this is our course table, and this is our enrolls table. So this enrollment date became a part of your enrolls table, right? Now if we go for a particular cardinality constraint, that's a many to any, many to one, right? The same is true for one to many relationship also, but we are discussing here only the many to one. Okay, so the student to course, it's a many to one, means a course can have many students, whereas a student can enroll for only one course, right? That's at most one course. Okay, so what we say, a course can have 0 to n number of students, whereas a student can be enrolled for at most one course, okay. So how do I represent it? The rule is like that the primary key of the one site becomes an attribute of the many site. The primary key of the one site becomes an attribute of the many site. Okay, what is that? So one side is course, right? So what is the corresponding table? So course is having two attributes, course number and course number. This is the simple way what we do, right? Whereas for student, we are having the student number, student name, and the course number, which is the primary key of the one site, that becomes a part of this table. And we don't have to create any table for the relationship set. So how it is possible? Let us consider the student table. So in the student table, we are having the entry student number, student name, and course number, right? So if I consider 101 is Raj, he is opting for mathematics. Now see, as the student number is a primary key of this table, we cannot have another 101 entry, so that I can associate it with CS 101 or computer science, right? This is not possible, as there can be only one entry for 101 for the student table. This student number is a primary key. That means 101 can associate with one course only, right? One course only, or at most one course only. If I want to say 102 Sanat is not associated with any course, how do I mention? Here in the column, I'll mention it's a null, right? That means 102 is not associated with any course. If I want to say 103, right? 103, say Bhaskar is associated with CS 101, right? So he's opting for one course at most, because 103 I cannot reuse because it's a primary key. So I'm putting a constraint, right? The student can enroll for at most one course. If it is 0 course, then I'll put a null entry over here for the course number. So that's why you have to remember this particular column. This is basically a foreign key, right? Which is referring over here, which is referring to this course number of the course. But this has to be a nullable attribute. This has to be a nullable attribute. So if a student is not associated with any course, I'll make a null entry for the course number. Okay, let us consider a one-to-one situation now. So one-to-one can be treated either as a many-to-one or one-to-many, right? So if you look at over here what this ER diagram is saying, it's saying a department can have at most one manager, or at the same time a manager can manage at most one department. Now if I consider this is as a one-to-many, right? Try to understand this is actually a one-to-one. We are just assuming it as a one-to-many, right? So as per our rule, the primary key of the one side becomes an attribute of the many side, right? So if we look for this assumption, so department, it's having the department number and the department name, and the manager. So along with the manager number and manager name, it also stored the department number, which is the primary key of the one side. Now in case I consider now it as a many to one. So this is inside and this is one side. So what will happen? The primary key of the one side becomes an attribute of the many side. That means the manager now having the manager number and manager name, whereas department number along with the department number and department name also have the manager number as an attribute. We'll consider now the cardinality constraint with the participation constraint. So this double line basically represents a full participation. So it says the student having a full participation in enrolls. So student must enroll for at least one course. That basically our participation constraint is, right? Whereas this cardinality is saying a student must enroll for at most one course. If I combine the cardinality as well as the participation constraint, that means a student must enroll for exactly one course. Minimum is 1, maximum is 1. Minimum is 1 for full participation and maximum 1 for as it is a many to 1 cardinality, right? Whereas a student course can have 0 to any number of students. So how we can represent it? So first we'll let us treat it as a simple many to one situation. So many to one situation means the primary key of one side becomes an attribute of many side. So the course in a simple way having the course number and the course name, at the student and the many side along with the student number and student name, will also consider the course number as an attribute as it is the primary key of the one side. Okay. So now the student must associate it with one course, exactly one course. So it cannot associate it with a null, right? So that's why this has to be a not null, right? This has to be a not null. At the same time, this is a foreign key referring to the course name inside the course table. So this is a foreign key which is having a not null constraint specifically. Okay. So this is full participation on both the side and it's a one-to-one situation. This is a very special situation where the entire thing can be presented using only a single table. Only a single table. So we'll basically combine all the attributes for both the tables and create a single table. So I'm naming the table as a mgr underscore dpt, so which is having the primary key from this table, primary key from this table, and all other attributes, the manager name, department name. And this basically the composite key, right? The manager number and department number. So you need to understand, as they are part of the composite key or they are the prime attributes, this manager number or department number, they cannot be null, right? So that means I'll be forced to associate a manager number with at least one department and a department with at least manager. So again I repeat, as this manager number and department number, these are the part of the primary key. It's a part of the composite key, right? So they cannot be null. So that's why a manager must be associated with at least one department, and department must be associated with at least one manager, right? So this is how we can show the full participation on both the side in a one-to-one situation. Now in this example, we'll consider a weak entity set. So here, if you consider the example, this section is a weak entity set, right? So whenever we are having a relationship with an weak entity set, so this course is related with the section. Section is the weak entity set. You have to remember it must be always a 1 to n or 1 to many cardinality, right? So that's why the normal rule for 1 to many cardinality, what we have learned, that is also true over here. So what was that? The primary key of one side, the primary key of one side becomes an attribute of the many side. So if you look at the strong entity, which is the course, which is on the one side, right? So we are having the course ID as a primary key, and the title is another attribute, right? Whereas in the section, which is the weak entity, we are having, along with this section ID, semester and year, this course ID also becomes an attribute of the section table. Now, as it is a weak entity, it's supposed to have a partial key, right? So partial keys are underlined, right? It's a dotted line. It's a dotted line. So you can see this partial key is a composite key here. So the partial key made of three attributes: section ID, semester and year. Now to construct the primary key of the weak entity, we must combine it with the primary key of the strong entity. So that's why the primary key of the section will be a combination of the course ID, which is the primary key of the course, and the partial key of the section, which is a combination of section ID, semester and year. So this is the total. This totally represent your primary key, which is also a composite key over here. Okay. Till now, whatever the relationship we have considered, all are binary. So this is the first time we are considering a ternary relationship. So in this ternary relationship, so we are having the strong entities, entity sets, teacher, project and student, and a relationship set, that's the project guide, which is relating all these three entity sets. Now to generate the tables or translate them into the tables, the same rule for binary relationship in case of many to many also holds good over here. So what we do for teacher, we'll just convert it into a table having the same attributes: the teacher name, which is the primary key, teacher number, which is the primary key, and the teacher name. Now the student, it also becomes a table having the primary key, student number, and the student name is another attribute. Then we are having project. Project number is the primary key and project name another attribute. Now this relationship set also becomes a table for us. Now what this table will consist of? It will have the primary key of the teacher table. It will have the primary key of the student table. It will have the primary key of project table and the descriptive attribute over here, that's basically the scenes, right? And what is the primary key? The combination of all three primary keys creates a composite key of project guide table, right? So this is how we convert a ternary relationship, which is given like this, into a relational schema. Okay. So next we consider a scenario of aggregation. So here we are having a ternary relationship with, say, a teacher can guide some students for a project, right? So this is the project guide relationship set. Now what extra we are having, so each project guided by a teacher for a student can be evaluated by an examiner, right? So this is the aggregation, right? So which basically creating this particular relationship set which we are calling evaluate, right? So evaluate will have the information of the teacher who is guiding a particular project for a particular student and the date of evaluation. So this is the information has to be done. Along with that, it will also keep the information who is the examiner, right? These are the information has to be kept into our evaluate table. So now you need to understand that aggregation creates a relationship with a relationship set. Normally we'll see that relationship set creates a relationship between two or more entity sets. But in case of aggregation, we'll see we are having a relation with a relationship set. Now, as you know, the table for this teacher will have this teacher number and teacher name. I haven't shown it explicitly over here. The table for project will have the project number and project name. Student will have student number and student name. That is the what simply we do. And the project guide will have the primary key of from all these three entity sets along with the descriptive attribute over here. So we are having the teacher number from the teacher table, student number from the student table, project number from the project table, and the since, right? And this becomes a primary key, this combination of all these keys. Now you need to consider this particular evaluate this particular relationship set as simply like a many-to-many binary relation between a project guide and the examiner, right? So the primary key of the project guide that becomes a part of it. So this part is the primary key of the project guide and the primary key of the examiner, right? Along with the descriptive attribute of this, which is this one. So this basically create your evaluate table, right? Now what is the primary key? The primary key of project guide along with the primary key of the examiner create the composite key. So this combination is basically your primary key, right? So this is how we'll have our evaluate. Now for examiner, again it's a straightforward way. We'll have the examiner number and examiner name. So in the next slide, we'll see all the relations, right? So for teacher, we are having the teacher name as teacher number and teacher name. For student, we are having the student number and student name. For project, we'll have project number and project name. For examiner, we are having examiner number and examiner name. For project guide, we are having the primary key of teacher, teacher number, primary key of the student, student number, primary key of the project, project number, along with the descriptive attribute for project guide, right? That's since. For evaluate, we'll have the primary key of the project guide, that is this part, which comes over here, plus the primary key of the examiner table, that is this, along with the descriptive attribute for this particular relationship set. Okay, we'll start with the specialization in ER diagram. So it's basically a easy relationship. So like in this particular relationship, we can say a faculty is a person and a student is also a person. So if you consider a university scenario, so the person entities can be of faculty type or it can be student type. Okay. But there are certain constraints in specialization. So they could be overlapping or disjoint. They can be partial or total. So we'll see them one by one. So first, let us consider what we are saying about overlapping here. Right. So we are considering our person entities can be of faculty type or they can be of student type. But we are also considering some kind of entity in our university scenario. They are of TA kind of people, right? Who basically sometime teaches, like they will be like acting like a faculty, and sometimes they act like a student. They take a role of a student, right? So there can be some person who are of both the type. They are also faculty type. They are also of student type. Okay. So there can be some entities which are of both the types. So that's it is overlapping. What is partial? As we have discussed, a person entity can be a faculty entity, it can be student entity, or it can be of both the faculty and student type. You can also have an entity which is only of a person type, which is neither a faculty nor a student, which just takes the attribute of the person type, right? So in this particular scenario, which is overlapping and partial, how we can create the tables? Let us consider the person having two attributes. ID is the primary key and name is another attribute. Now faculty, what a faculty having in extra, they are having some salary. So what is the extra thing we have added over here? Now whenever we need faculty information, we can perform a join between these two tables, right? It's a natural join. So what will happen? It will fetch the ID, name and the salary for a particular faculty, right? Now for the student table, what we have extra, the students are having certain grade, right? So whenever we need a student information, we perform a join between person and student, right? We'll get the student ID, student name and the grade. That's done. Now if we consider the tables like this, every time we want to fetch the faculty information or student information, we need to perform a join, right? A inner join has to be performed. So which makes the operation a bit costly. So if we want to make it more efficient, so we need to compromise with the redundancy, right? So we can let certain redundancy in the table so that we can have a better efficiency. So how we can achieve that? We can make this name redundant in the all the tables, right? So whenever we want to fetch the faculty information, we have to just search into the faculty table. We don't have to do any join with the person. And whenever we need the student information, we need to search into the student table, right? And as there can be also entity which are of person type, so whenever we need some information about a person type entity, we have to search on the person table. That's all. Now the second scenario. Now in a university scenario, we consider the students will be either of a undergraduate student or they can be of postgraduate type student, right? Okay, so the partial, as we have discussed, some student can be undergraduate type, some student can be a postgraduate type, and some can be just their students. They cannot be categorized like a undergraduate or postgraduate. They're just a student. Some, yeah, general students. Now what this disjoint means? Now a student cannot be at a time both a undergraduate student or postgraduate student, right? They're disjoint. So they have to be either a postgraduate or a undergraduate student. This is the scenario. But the table representation will be similar what we have seen before. Say the first case, the student having a student ID and student name. What undergraduate student having extra, that's a project marks, and a postgraduate student having extra thesis marks. So whenever we need information about the postgraduate student, we get the postgraduate student ID, the project marks, and we make a join between the student table and undergrad student, and we'll get the name also. Similarly, whenever we want information about a postgraduate student, we get the ID of the postgrad student, thesis marks, and if you want to get the name, we have to make a join with the student table. Now again, every time we need to fetch the information about the undergrad student or a postgrad student, we need to make a join, right? Now, if you want if we want to increase the efficiency, we need to permit certain amount of redundancy over here. So name will be redundant over here. So if you have to search information of undergrad student, just do inquiry inside this. If you have to find the information about postgrad student, just make a searching on this particular table. Okay. Now considering a scenario which is of complete type, so along with complete it is also disjoint. But this is especially this complete thing is significant because the same kind of situation we need to consider whenever it's a overlapping and complete also. Now, a part entity can be a purchased part or it could be a manufactured part, right? Now, want to say disjoint means they cannot be neither like both manufacture and purchase. They have to either purchase or manufacture. They cannot be both, right? That we have seen already. But the complete says each of the part has to be purchased part or manufactured part. They cannot be just a part, right? There cannot be any entity which will be of the part type. There has to be either of the purchase type or of the manufactured type. Now, in the case of complete constraint, there is no point to create a table for the parts, right? So that's why for part we are not creating any table. Rather that the part which is having two information, that the part number and the part name, that will go into purchase part table and manufacture part table. So these are the common, which are the attribute of part table. Along with that, we are having the extra information, like for purchased part we are having the price and vendor. For the manufactured part, like from which department the particular part got manufactured. Okay. So here we come to the end. So in this particular tutorial we have discussed starting with a ER diagram, how we can convert it into a relational schema. So thank you for watching.